Alright, another draft science presentation. Pake Physicser of the Week, part 2. Just a versus video, really, so maybe I'll just retitle it to a versus part 2. But anyway, doesn't really matter. Just more talk on gravity and an attempt to make some sort of reasonable explanation of what there's evidence for and what is just storytelling, talk, and such.
Hello again. I am talking about gravity. If you haven't seen part 1, where I introduced Einstein's thought process and the equivalence principle, go and watch that video right now. There'll be a link down below that you can click. Otherwise, what I'm about to say is not going to make nearly as much sense as it needs to.
Yes, well, it still won't make any sense, and it really don't need the part 1 because it doesn't say anything in the part 1, so whatever. Certainly doesn't cite an experiment in part 1.
If you haven't watched part 1. So, don't worry, you know, I'll wait here, no big rush. You're back? Okay, good. Let's get going. So, in the first video, I talked about the equivalence principle, how there's this connection, this relationship between inertial mass and gravitational mass.
Okay, and again, there's no reason to believe there's any such thing as inertial mass and gravitational mass. I mean, inertial mass is basically saying something stupid like, let's just pretend you don't have a velocity because you have the same velocity as the stuff in the room. I mean, that's not saying anything reasonable. It's saying, let's pretend. Let's pretend the truth isn't the truth.
And how they're the exact same. And how Einstein said, quit trying to worry about it, just make it a thing.
It can't be a thing because there is no opposite. Nobody ever thought that inertial mass was different than any other mass. There was only mass. There's no inertial mass. There's just mass. You either have it or you don't have it.
These two masses are identical. What can we learn? Well, we can learn a few different things. Imagine. And these are Einstein's original thought experiments, by the way, that helped his thinking, leading to general relativity or modern understanding of gravity.
So thought experiment is just a replacement for experiments we can't do, and experiments that we can just make up the results of because they're not real experiments. So we can just make up what happens.
Imagine you're a worker, like a construction worker, on a very tall building, and you fall. Now, Einstein is pretty dark here, but it's a useful thought experiment.
Right, it's not a thought experiment. That experiment has been conducted. Many people have fallen off of bridges, so the experiment has been done.
So we're going to follow what Einstein says. Imagine you're falling from an office building, a very tall construction, a skyscraper. As you're falling, take away air resistance. That's something we don't need to worry about here because we just want to look at gravity. We don't want to look at anything else.
Right, but the air resistance is what's going to make you have a sensation because that's going to create an obstacle to your gravity, which means it's going to create some opposing force that's going to push on you. So you're going to notice that the wind is going 120 miles an hour as you're falling, and that wind is going to feel like pressure.
Boy, air resistance. You feel weightless, don't you? You don't feel...
So again, you don't feel weightless, you feel unburdened by gravity. And I suppose one could argue there's a difference. It's not that you're not, you can't only feel acceleration if there's something opposing it. If you are accelerating, your acceleration is not being opposed, therefore you're not going to feel it. But you're going to feel it when you're being accelerated, say, by being pushed, by somebody actually physically pushing you. You're going to feel it. Now, if somebody pushes every atom inside of you, you're not going to feel it.
Gravity. We've seen this. You see videos and pictures of astronauts orbiting above the Earth. They're in a constant state of free fall. They're always falling. They just happen to be missing the ground all the time, so they stay in orbit. But they're constantly in free fall, but they look weightless. They look like there's...
Yeah, but the concept of weightless doesn't mean much when the fact is the thing is accelerating and gaining velocity with every second. So the fact that what it feels doesn't necessarily have anything to do with what's actually physically happening. And again, if the force that's pushing you is a rocket ship, it's going to be very different than free falling in gravity or an elevator, because you're going to actually feel the floor pushing against your feet. You're going to feel the source of the gravity, where when gravity's pushing you, you don't feel it one place until the opposing force shows up. So without the opposing force, you can't sense the gravity because it's not pushing your eyeballs faster or slower than it's pushing your feet.
No gravity anywhere near them, not even touching them. They look like they're in the middle of nowhere. How can it be? How can it be if the gravity of the Earth is pulling on an object? It's affecting you, like it's causing you to fall, and yet you feel like there is no weight at all.
Right, but the only thing we're talking about here is you're saying that gravity is a force that's only affects something when it's moving, and the point is that no, gravity affects things when they're not moving. So if I put you between two planets, equal planets A and B, and they're both the same mass, and you're equidistant between the two planets, you don't feel any pull. But the fact is you're being pulled by both. So gravity is really, you can understand it pretty simply as something you only see or sense when there's an imbalance in the force. That's it. So it's just an evidence of an imbalance in force, not necessarily the absence of force. So when the forces are balanced, you're free. And when they're not balanced, you're moving.
The way that works is through the equivalence principle. If inertial mass and gravitational mass exactly cancel out, that means...
Again, there is no inertial mass. What is inertial mass? There's only the electrons and protons you're made of. They have atomic weight. That's your mass. There is no other measurement of mass, unless you're just going to use some stupid scale argument. And if I'm moving the same speed as my scale, I can't possibly dent it. The bullet, you're saying that its inertial mass is 10,000 pounds per square inch, because when it's moving, that's what it is. I mean, where it impacts is going to be a tremendous amount of weight. Well, that doesn't mean the bullet actually has that weight. That's just a measure of momentum, not actual mass. I mean, you've got to draw a distinction between measuring something's momentum and measuring something's weight or its mass. These aren't the same thing.
If you are in free fall, you are weightless. You are experiencing zero gravity, which means.
So again, you're obviously not experiencing zero gravity when you're being accelerated and your velocity is continuing to increase. it's like I said, the fact that you can't feel gravity is just because it's not a rocket ship pushing your feet first. You don't feel the force move through you, but in the rocket ship, you're going to feel it.
To you, it looks like the flat space-time of special relativity. You appear, in the jargon, you appear to be inertial. You have an inertial frame of reference, which is exactly the kind of reference frame you need to make all the mathematics of special relativity work.
Right. There isn't all this much mathematics, and the mathematics really just has to do with the associating time, throwing time into space, and bending time. And it's totally unnecessary, and absolutely no evidence saying there's any hard relationship, anything called time. There's a hard relationship between telling time, that is clocks. So you can break certain clocks with velocity. And the clearest example is atomic clocks. Now, we really don't have any real evidence that standard clocks, clocks that use a crystal or clocks that use a pendulum or sundials, that any of those are in any way proportionally by any Einstein law time dilated, because any movement of those clocks breaks them. They break really easy. So this is just about what breaks clocks, and the fact that atomic clocks, things that are dependent on atomic decay, do have a proportional decay rate that fits into it fits the same curve. You could argue an inverse square type curve.
Now that's a clue. By starting with the equivalence principle and thinking through a particular situation of free fall, special relativity pops out. When you start thinking about the problem...
Says you. So again, just there's nothing pops out, nothing fits really. It's all mostly just pretty words and pretty jargon, and no real hard evidence of any of these relationships. Again, there's no relationship between something called time. There's no evidence that time is a dimension or a place that can be bent or warped. And all there really is evidence of this is you can break some clocks, some mechanical devices will misfunction if you give them velocity, and they'll do it at a certain proportional rate.
Of gravity, and you dig a little deeper, there's special relativity sitting right there. Aha, that's a clue. The next clue comes with a slightly modified thought experiment along the same
There's no clues here at all.
line. Let's say you're in a rocket.
You have no clue.
Rocket, and you have a laboratory or a house or whatever, and you close all the windows, and it's a perfectly silent engine. There's no vibration. There's no noise. Again, this is a thought experiment. We're idealizing the situation so we can understand the nature of gravity.
Yeah, so you're not going to understand anything with this preposterous idealization where you say you can't look out the window, you can't do this, you can't do that, you can't do anything. And then you're going to talk about doing physics experiments where physics experiments are sort of dependent on you having interaction with the world. So you're going to close the system, pretend to close it, and then make a declaration. And again, the declaration, in my opinion, is just totally false in the sense that you're saying basically, I can agree that all the chemistry within the confines of your frame, that is the other atoms being moved at the speed you're being moved at, they're all going to be at some sort of inertial starting point. They're all going to have the same absolute velocity. If you're sitting here together, you must have the same velocity. So you're going to be affected by physics all the same by that physics. So you're going to be time dilated the same amount, you're going to be retarded the same amount, whatever. Everything's going to be the same for you until you change something within that environment. So essentially physics works. But physics isn't going to work when you apply something like a force in that environment, because the force only exists in one universe. The force doesn't exist in your frame. It exists in an absolute universe. It has an absolute geometry. It has absolute motion in directions. It travels absolute amounts of distance. It's not going to obey your rules of frame. So the point is that Einstein's thought experiment was basically the invention of the light clock, the idea of shooting light perpendicular to your motion, and what would happen to the light? Well, the light would appear to fall because the side of the ship would be moving, and so as it moves, the light's going to hit a lower point than what perpendicular actually was. So perpendicular is here, the light's going to hit below perpendicular because in the time it takes the light to get across, the ship has moved. That's the thought experiment. The light doesn't actually fall. It will appear to have done that. And so to make everything equivalent, Einstein said photons do the same thing on Earth. And to make them equal, he decided that the force of gravity must be twice as strong for photons than it actually is to gain that equivalence. And so he just made up some facts of the universe that aren't proven to be facts.
We don't want any distractions. In this lab, what would you do? Let's say you're in this lab and the rocket blasts off and you're in space and for a moment you're weightless. And then the rocket really gets going. It really gets going and it starts accelerating. And it accelerates at exactly 9.8 meters per second squared. The exact same acceleration call.
Right. So as long as you're away from the Earth, that is, you're not being pulled by some other gravity, then that will feel like you're on the Earth because the bottom of the ship is going to be doing exactly what the Earth is doing to your motion. It's going to stop it. Okay, so there's a force pushing up, and in the case of the Earth, there's a force that's not pushing up. You're crashing into it. Your velocity is into the Earth. So the two things are going to seem like the same difference, whether the Earth is moving towards me or whether I'm moving into the Earth. Well, yeah, that's like a 7-year-old could figure out that those two things are pretty much the same thing. Me moving my face into your fist is the same as you moving your fist into my face. If the speeds are the same, the outcome is going to be the same. But that doesn't mean gravity is the same as being accelerated in a rocket ship, because it's not, because gravity affects you differently than the force hits you differently than the bottom of a rocket ship hits you.
Caused by the Earth's gravity. Now, could you perform any experiment inside your little laboratory in the rocket ship with no windows, no sound, all that? And could you tell if you were still in the rocket that was accelerating at 9.8 meters per second squared, or you had landed back on the Earth. And you were
Right. So if Einstein's wrong and gravity doesn't bend light and doesn't bend it at twice the rate it bends everything else in the universe, then you could tell is the simple answer, because you could see the side of the ship move and you could see the light fall down, and it would essentially be a speedometer. The faster you go in the ship, the more the light attempting to go perpendicular, so the more the light going perpendicular would fall. So if you put a little spot on the side of the ship where perpendicular was, the further away from that spot, the faster you're going. So essentially light would be a speedometer and would tell you how fast you're going. And you would know you're moving and the rest of the world isn't moving. So you would know that your velocity is really your velocity and not the universe's velocity. And so if Einstein's wrong, you have your answer.
We're just feeling the Earth's gravity. Well, what could you do? Well, you drop things. I don't know. You pick up your keys, drop them, they fall to the floor. Now, here on Earth, they fall to the floor because gravity's yanking on them. But in the rocket ship, if you could peek inside, if you were standing outside the rocket ship and looking at this little laboratory.
So, and again, yeah, that's fine. So, yeah, if you're working with other material objects made of the same stuff you are, matter, then the laws of physics are going to be the same. But the point is that, I mean, they're going to be the same problem of it's going to seem the same pushing up and pushing down. But the fact is, moving light is a whole different thing, right? Because in the spaceship, the light isn't moving. And in the gravitational well, the light is moving. So there are two fundamentally different things happening.
Experiment going on, the keys would stay in the same place. Like, say you drop them here, but then the rocket ship would move and meet them and then press them up against the floor and carry it with the rocket ship. But from outside the rocket, you immediately know what's going on. You say, oh, it's just the rocket accelerating. It's no big deal. Inside the rocket, though, you couldn't tell. Because either way, whether you're on the ground or inside the accelerating rocket ship, either way, the keys fall to the ground. And now you start getting really clever. You're like, I know, I'll get different masses. I'll get the keys, and I've got this bowling ball over here. Why I brought them on a rocket ship, I'm not going to worry about that.
Right. None of that would do you any good, because obviously gravity proportionally affects, and so does acceleration in a rocket. It takes more rocket fuel to move something heavy up to space than it takes to move something light. So we already know that those two are going to be equivalent also. And so again, the point is that the physics experiment you could do would be to make yourself a light clock, and that will tell you how fast you're going, because the light's going to be a standard to the universe. It's not going to care about your frame, and it's going to tell you the truth about whether you're moving or not.
And then something bigger, and I'm going to line them all up perfectly horizontally, and I'm going to let them go, and they hit the floor at the exact same time. Just like Galileo's experiment a few hundred years ago. From the perspective outside the rocket, it's easy to see why. The rocket doesn't care about the masses of whatever you're dropping, because they're just floating.
Right, because they're not dropping is the whole point. They're not collecting more force. They're not doing anything, because you're just raising the floor at the same rate towards the two objects. So, yes. But if you were inside the bowling ball, okay, you would be able to tell that you're not creating the motion, because if you had a light clock, you'd see that the perpendicular light beam just goes straight across. I mean, a light clock that would work for slow speeds. Obviously, it's not enough of a difference so at slow speeds you'd never be able to use photons because they move too fast. So photons only work if you're going really fast.
Being still, boop, 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 lining up, and then the rocket's floor comes up to meet them, and then they stick to the floor, and then they continue to be carried on with the rocket. So the rocket doesn't care.
But the rocket will care in the sense that the rocket will be dented more by one object than the other, because it's going to be hard to push it. So there will be weight on the floor that will signify the weight of the objects.
About mass. Here's Einstein's insight. Gravity causes acceleration. We're totally used to that statement, right? Just there's gravity, there's a gravitational field, you can drop things, causes an acceleration. No big deal. Through the equivalence principle, where inertial mass is the exact same thing as gravitational mass, Einstein was able to flip that around. He was able to flip that around. Acceleration causes gravity. I'll say that again because that is such...
Yes, and it's just wrong. Because the only way acceleration creates gravity is things accelerating towards you, in frank truth. Something has to absorb force for you to feel the imbalance. Gravity, let's understand, is just an imbalance in force. Something has to imbalance the force, and the way it gets imbalanced is by something heavy getting in the way of the force moving towards you because it's absorbing the force that would have hit you. Now that force doesn't hit you, so obviously you're getting hit more from behind than you are in the front because something absorbed the force that was going to hit you, just like if it was light. If they absorb the light doesn't hit you, you're not getting hit by the energy. That means the light that's hitting you from the other side, if both bulbs were equal, the thing shattering you is obviously going to cause an absence of force, which means you'll have to move in the direction of the absence. And when you move in the direction of the absence, you're going to absorb force, and that force doesn't hit the thing that was coming at you, and that's going to make gravity for that thing. But there has to be a real force, and that's how it really works. There's a real force absorbed to create gravity. You can't create gravity unless you imbalance the field, and you have to imbalance a field by collecting something, by taking it out of the field, by absorbing it.
A deep insight. And Einstein made this insight way back in 1907, 7 years before finally developing general relativity. Acceleration causes gravity.
So again, it's not true. An accelerating bullet doesn't create gravity because it's a different force. Okay, that it's an explosion that causes the momentum. So it didn't absorb force that would have hit you. There was no force that would have hit you. The explosion is a new event in the universe. It wasn't some force that was heading right for you in some balance. So now it's creating an imbalance in a force imbalance. But it's not an imbalance because of a shadow. So it's nothing like gravity in that sense, in that you haven't changed the equilibrium. It's the wrong way to say it. You've obviously changed the equilibrium. You didn't change it by subtracting from the existing field. You changed it by adding to the field. So it's not going to be technically gravity. But clearly the bullet bores a hole in you just as if gravity had done it.
It causes acceleration. Acceleration causes gravity. If you're inside that rocket and it's accelerating, you are experiencing gravity. It's happening.
So again, you're obviously not experiencing gravity until the floor is actually pushing you. And that's not gravity. You're just experiencing another force hitting you. A force completely different than with a force of gravity. You're being hit by a substance, and that substance is pushing your matter, and it pushes the cell against cell, atom against atom. It's not doing it in a nuclear way, wherein gravity is affecting all the little bits inside of you.
Into you. You're being pinned to the floor. And this is where we get the picture, the sense, when we say gravity is a quote-unquote fictitious force. It's a
So again, this, as you say, right, so what rational science person, I mean, if Newton had said some kind of silly thing like that, a virtual photon, or if he would have said a fictitious force, let's pretend a virtual force, everybody just would have said, shut up. That's not physics, that's not science, that's bullshit. Let's play make-believe, pseudo-force. You couldn't have gotten away with any of that crap, because science had some integrity back then, and it lost all of its integrity in 1930.
Fictitious force because you want. Your natural state is to be in freefall. Gravity, acceleration.
No, your natural state, so to speak, is to be in balance. So if I just put you in the universe, you're going to be getting hit by a ton of force. It's just going to end up being balanced. You're going to get hit by as much this way as this way, this way as this way. So you're not going to do much. You're just going to sit there and vibrate in the subtle, different, tiny little differences that will occur over time. You know, there'll be, it's like heads and tails. Every now and then there'll be 50 heads and 51 tails. So you'll be moved a little this way. And then the balance will go back the other way. And so you just jiggle a little. But that's it.
It's all the same you want to be in freefall. It's only until you meet the floor that you feel the effects of gravity. But the force that's providing that feeling is actually like the atoms and molecules.
But no, the force that's providing the feeling is the absence of force, technically. So what's really moving you is a deficit in the force because the Earth absorbed it. So the Earth has absorbed energy. It technically moved towards you in a sense. And that movement towards you absorbed energy, and now you're going to fall into the absence of energy. you're going to be pushed because there's more stuff coming from up there than it's coming from down there. And you're technically going to be pushed by the greater pressure up there than is down there. And the same thing, right now I'm moving towards the center of the earth, and that movement pushes on the earth and makes pressure below me. And so while I'm making that greater pressure, somebody in China is doing the same thing to me. Okay, he's making pressure in this opposite direction. And he's absorbing energy that doesn't get to me. If there was no planet in the way, and no other person on the other side of the earth, then the energy would get to me. I'd have an equal amount of force hitting me from below as I do from above, and I wouldn't be moving anywhere. But because he's absorbing it in the sense that he's moving and creating pressure, and that force doesn't get to me, therefore I have to move into the low pressure.
Molecules pressing up against each other and resisting each other. That's what gives you your sensation of weight. It's being pressed up against this chair or down against the floor. Exactly the same as if you're in a rocket ship and you're laying on the floor and the rocket is pushing and you can feel the rocket.
It's not exactly the same at all, but in a sense, the sensation you're going to feel once you hit a solid object, and now you're going to be feeling the atoms pushing against atoms. So you're not going to be feeling the gravitational force. You're going to be feeling the atomic force, the pressure, the force that's opposite your gravity, the opposing force. That's what you're feeling, the opposing force. You're not feeling gravity, you're feeling the opposing force.
Pushing you, it's the exact same thing, 100% identical as gravity pulling you down.
So again, it's not 100% identical. The gravity is a nuclear force. It's affecting electrons and protons. The physical impact force of having a floor hit you or a chair hit you or whatever you having hit you as you're attempting to fall, as you're attempting to get to the center of the earth, as you're moving towards the center of the earth, and you're being stopped from doing that. That's a physical mechanism that has to do with the pressure inside of atoms and not the pressure being exerted by gravity, in the sense of it's not a nuclear force. It's a material. It's not a force, but there's just a difference between acting on atoms and acting on the bits inside the atoms.
Gravity causes acceleration. Acceleration causes gravity. These are identical. So free falling observers.
They're not identical, blah, blah, blah. Acceleration does not cause gravity. I don't know why he's saying that, because, I mean, there's lots of examples. I'm accelerate this piece of stuff that doesn't create gravity when I'm accelerating it. The only way you can create gravity is this thing has to move, not because I push it, but because it absorbs field energy that would have gone over here. So until it absorbs gravity, it can't create gravity.
Free fallers experience no gravity, zero gravity.
So again, it's not. There's obviously when you're moving, you can't be not being affected by a force. So you can almost say right from that, this idea of it being free is kind of stupid because it's clearly accelerating. So when you're falling, there's no such thing as free falling, because to do the falling part, to do the accelerating part, to do the gaining velocity part, you're obviously not in a free environment, which is usually free would be unaffected or uninfluenced. It certainly wouldn't be something you call imbalance. Imbalance and free aren't synonyms. And clearly you're in an imbalance in force if you're falling.
And acceleration causes gravity. So these are the pieces.
Notice it's just nonsense. And I don't even think Einstein would like that as a paraphrase of his theory. Frankly, I don't think that's what Einstein really thought.
Einstein was starting to work with to understand general relativity, where special relativity was there, hiding in the corners, and there's this unique connection between gravity.
Yeah, look, the two theories are really just about acceleration, and one of them makes a distinction between a gravitational component, and the other one makes a distinction about just velocity and time dilation. So the two aren't exactly, I don't know how to say it, but the irony is the two theories are opposite each other, in the sense, in one theory we become more time dilated, and in the other theory we become less. And that's one of the ironies of it, is the two actually I don't know how to say this, but the real point is that the gravitational component is the one that has the greater influence, because the gravitational component is the one that's really making us go faster than the satellites. And it's making us go faster in the sense that we have to cover more distance, because your atomic bits, as you might understand, are still moving down, and then they get pushed back up in the other direction. So the forces are active inside of you. So there's bits of you that are heading down, and there's bits being pushed back up by the pressure of the Earth. And so essentially your bits are bouncing. And if I bounce you and then move you in a direction, your total velocity has to greatly increase. So I've used this analogy, but the basketball player could be running 10 miles an hour, but the basketball is probably going 50 miles an hour, because the basketball is covering so much more distance, because it's going up and down as it goes 10 miles an hour.
And acceleration that doesn't exist with any other force. It just doesn't work. Now, where do you go from there?
So again, just nonsense. It doesn't work. Of course it does.
It's not quite a full theory of relativity, is it? But it's getting closer. But the closer is going to have to wait till the next video. So I know it's a long series, and usually I don't do these series, I promise. But just general.
Yeah, long series. 4 10-minute videos. I guess there's 4 parts. So should I do part 2 now, or 3? No, I think I'll wait, because I feel like it. Or don't I? Do I or don't I? Yeah, let's do it now. Let's get it over with. Part 3. I have to get rid of the commercial.
Visit California.
It's very instantly.
Well, I have to
Like
wait
all of it,
for
not
it to
just
go
this.
away.
No, but this is pretty good though, isn't it?
Yeah. 2 commercials. Pretty annoying. Very annoying, but what do you
Welcome
do?
back. This is part 3 of a probably 4-part series on general relativity. It could be a lot longer, trust me. If you haven't seen the first 2 videos where we're exploring Einstein's thought process that eventually brought us over the course of 7 years to general relativity between the years of 1907.
Well, let's just understand. His thought process was to concede the point that the light clock, he doesn't say the photon jumps to the future to hit the mirror. Basically concedes the photon falls as the side of the ship leaves. So, important. It's a very important fact, because he forces light to do the same thing. And so if he believed it jumped to the future, then he wouldn't bother forcing light or photons to be bent by gravity.
Then in 1914, you should watch those other 2, because this is just one of the puzzle pieces of general relativity. If you don't have the other 2, this one doesn't make so much sense. So in the first one, we explored the equivalence principle, how inertia and gravitational...
So again, he hasn't cited a single experiment in all of this conversation, beyond thought experiments, and the simplest of them are obvious. That, so it's almost a straw man argument, in that nobody was arguing that the force of gravity breaks down or something, or somehow different masses don't fall at the right rate, or some other kind of... Nobody's arguing any of that crap. And so it's just all this pigeonholing and strawmanning, a fake argument that somehow Newton didn't know what relative motion was, when of course he did. And what he didn't have was any evidence that there was no such thing as absolute motion either. He had nothing, there was no evidence that there was no such thing.
masses are exactly the same. So a falling object experiences no gravity, and we learn.
So let's understand, a falling object is experiencing an imbalance in the force, and that's the definition of gravity. So imbalances in force create motion. That's what gravity is. So clearly it's not being unaffected by force. It's being affected by force. It's just not going to be able to sense it because the effect is taking place on the subatomic level, not the atomic level. And it won't be until it interacts with physical matter that it can have an interaction that it can sense where it's actually going to be able to feel it, because it'll be a force that's going to contact the matter, not just the elemental bits of the atoms.
That gravity is acceleration. They are exactly the same.
And again, that's just nonsense. Gravity isn't acceleration. Gravity is an actual force that causes acceleration. And other things can cause acceleration, like rocket engines and all kinds of, wind and all kinds of things can cause acceleration.
And we learned how special relativity is hiding underneath the surface when we start exploring the nature of gravity, because a free-falling observer experiences no gravity, which means they...
Again, it obviously is experiencing gravity because it is falling, which is evidence. It's accelerating, which is all evidence of a force acting on it. So it's just silly to say it's not experiencing gravity when it's in the process of being gravitationally moved.
Special relativity applies to them. Now, the third major piece is a little bit harder to visualize. It's another thought experiment, courtesy Uncle Albert himself. It's a little bit harder to think about, but it's a very necessary one. And this one is where you imagine something like a merry-go-round. Like, the spinny thing with the horses that go up and down. Now,
brother.
Well, imagine you build a particularly weird one, where all the horses are perfectly nose to tail. Like, you leave absolutely no gaps on that outer edge, where it's horse, 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 all the way around in a circle. Lots of horses. Now, imagine what happens if you're standing on the ground and you spin it up really fast. Like, not just a little bit, but like close to the speed of light, really, really fast. Well, we know from special relativity that there are two interesting things that happen to objects that move.
So again, this isn't anything about what we know. This is just about the story they're going to tell. But it has nothing to do with anything known.
Moving clocks run slow, and moving rulers contract along the length of their...
Right, so there's no evidence that anything contracts, so it's just more crap. Again, time dilation is a fact, in the sense that we know that atoms decay slower when they have velocity. So if you move a decaying atom fast, it will decay slower. But I argue that that can just be represented by understanding that when something's moving, and let's say it was rotating, that its rotation would occupy a lot more space. The circles get bigger for the circles to process. So processing circles have more length in them. They have a bigger circumference. So obviously you could argue the metabolism of the atom, that is how many rotations it might have or how many times it might spin, would be tied to the fact that if it's processing, it takes it a longer period of time to make one clock cycle. So you could even make the spin of the atom or the rotation of the electrons. I don't really believe that takes place, but let's just say for the sake of argument it does. You could almost turn that into a clock and just say, obviously, if I make the clock have to process, it won't tell the same time because the length it has to travel is larger. Now, that's an isolated fact. You don't need relativity or any other bullshit tied to that. That's just in and of itself a theory of why there's a connection between the motion of an atom and how it decays. That's it. There's no bigger theory tied to that. You don't need to tie any other crap to that. That's just an independent fact. And all they're trying to do is take that independent fact and say, well, because this is true, all this other crap has to be true. None of it has to be true.
Motion. So that means if a 1 meter rod is racing by you at close to the speed of light, it will appear to be shorter, depending on how fast it goes, as it breezes by you.
So again, there's no evidence of any of this contraction. There's no evidence, physical evidence, that anything contracts in size because you give it velocity. None. Now you could argue that traveling through mediums, something could compress from its velocity. So if I move you fast enough even through atmosphere, you'd be sheared by the friction, and you might be compressed by the pressure at one end is going to be very, very high. Your head is going to, burn. It's going to get hot, and there's going to be a lot more pressure at one end, so you could be compressed by pressure. But there's absolutely no reason to believe. There's no evidence indicating that there's something fundamental that happens to atoms and they get smaller when they're processing. No evidence at all at a velocity.
As an unavoidable thing, it's a part of the relationship between space and time. It's baked into the very mathematics of special relativity. You can't get rid of it.
So again, you can get rid of it. All of these things can be completely a la carte. You can separate all these pieces of theory, doubling the effect of gravity on photons, the time dilation. You can separate each one of these subjects. None of them have to be in any package deal. There's no obligation to tie them all together and say there's something called space-time and this and this and this. And again, this is the big failure of this whole science, is the Eddington experiment, which didn't even prove anything. It only proved if it was even valid as an experiment, if it was even credible as evidence. Even if we concede it was credible as evidence, it only proved one tiny thing. It did not prove the entire theory. And the headline is Einstein right. The headline wasn't Einstein right about one thing. No, it was like Einstein was right about the whole theory.
So, when we think about this special merry-go-round, as it's going super fast, these horses are going by you, and when they cross in front of you, they're going close to the speed of light because we're really good at building merry-go-rounds. That means they're shorter, which means they're not nose to tail anymore, which means they're...
So again, there's no evidence this happens. There's no evidence that the gaps between atoms gets bigger. There's no evidence that anything does any of this crap. So this is just a made-up story.
They're gaps when there used to not be gaps. Okay, that's not such a big deal, except when you think about the relationship between the circumference of that merry-go-round and the diameter of the merry-go-round. When it's stationary, it's just a circle. And Euclid told us all about circles, that the circumference of a circle is equal to its diameter times pi. So you measure the diameter, multiply by pi, boom, 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 that gives you the amount of circumference. No big deal. But what about the spinning one? You built that circle. You built that circle perfectly, and you had no other choice because you're using, this is just Euclidean geometry, good old high school geometry. Now you accelerate it where the horses are smaller. There are gaps. Their circumference is larger than it used to be. The circumference is not equal to the diameter times pi. It's equal.
So well, that doesn't even make any sense, right? So you contracted the horses and somehow making the horses smaller and filling it in with extra space somehow makes the circumference larger. So that doesn't even make sense. So, yeah, sorry, that doesn't even make sense.
To a bigger number. And the only reason it does that is because it's spinning close to the speed of light. Well, is there any mathematics at all that describes that kind of situation where the circumference...
Is there any evidence that indicates anything like that ever happens? No.
So the circle doesn't always equal its diameter? Well, yeah. Non-Euclidean geometry. This is a set of geometry developed around the mid-1800s, relatively forgotten in the decades since then, until Einstein started thinking of these things. He started asking his mathematician buddies, like, hey, I've heard about this like non-Euclidean geometry. Can you tell me more about it? They helped him dig through the literature, work out some of the math, and the mathematics of non-Euclidean geometry is the mathematics of curved objects. Imagine like the surface of the Earth. The surface of the Earth is not flat. The geometry that you learned in high school, the Euclidean geometry, only applies to flat. Like here on this table, I can draw triangles, and the interior angles of a triangle add up to 180 degrees. I can draw two parallel lines, and the parallel lines stay perfectly parallel out.
Yeah, I know. 2-dimensional versus 3-dimensional. Is that all you're arguing? So, I mean, really, it was some mysterious thing that we had 3 dimensions. I don't think that's mysterious.
To infinity, all the usual stuff. Apply that to the surface of the Earth, and different rules apply. If I pick 3 cities on the surface of the Earth and draw straight lines between them, the interior angles of that triangle that I just made will be greater than 180 degrees. If I draw 2 parallel lines at the equator, like let's call them lines of longitude, because why not? At the equator, they start out perfectly parallel, and then the curvature of the Earth will force them to meet at the poles.
Right. But as a fact, you still could draw straight lines. You don't have to obey the curvature. So again, obviously a sphere is different than a cube. Yeah, duh.
Parallel lines don't stay parallel. Circles, the circumference doesn't always add up to the diameter times pi. Straight lines aren't always straight. Triangles obey all sorts of weird relations. This is the rules of non-Euclidean geometry of curved surface. And there's the final puzzle piece.
There's no puzzle piece. It's just nonsense. So, yeah, they're trying to put square pegs in round holes and round pegs in square holes. and saying, look, we can do it if we cheat. Fine. So what? Who wants to do it?
That Einstein needed to get us general relativity. One puzzle piece is that special relativity, flat space-time, is hiding there on the surface for free fall observers. It's always kind of there. If we always we roll back the curtain a little bit and like, okay, there's special relativity. So space-time is the language we need. Space-time is still the stage.
Whatever this baby talk is. There's no stage, it doesn't say anything. It doesn't explain how the electrons and protons know they're supposed to go that way. They're not told by anything. They're just automatically say, I have to go that way. Now, that might make sense to you as physics, but that doesn't make sense to me as physics. That sounds like spooky action, silly action, fairy action, angel action, God action. It doesn't sound like physics.
The second thing is that gravity and acceleration seem to be connected and seem to be identical. And then last is some kind of
So again, that doesn't have any evidence tied to it either. Obviously, this acceleration doesn't have anything to do with making gravity. It's nonsense.
Accelerations, like a spinning merry-go-round, lead to non-Euclidean geometry, aka curved spacetimes.
So again, curved geometry again. So Euclidean geometry is, we're supposed to believe, didn't include circles. So fine, you draw everything in straight lines. So you're basically just saying, I'm just going to create a world where there's no curved lines. Well, we know our world has curved lines in it, so it's not a huge leap. But I would argue that the elemental universe probably doesn't have any curved lines in it. And everything we see as a curved line is just an Elist line.
These pieces together that Einstein needed to make general relativity happen, or at least get started. It took him a couple more years to actually work out the mathematics of what this all meant.
So again, there wasn't any mathematics about what all this meant. There was really just mathematics to sit there and explain things like Mercury, to do something to prove it. So they spent some time working out the mathematics to demonstrate a proof. And you ended up with Einstein's field equations, which are so preposterously complex that, there's only a few people who've ever solved one in a real circumstance. As far as I know, I've never even seen anybody actually do anything but derive equations. I haven't seen them ever apply the equation to an actual circumstance with actual numbers, actual variables.
Actually take all these nebulous concepts and codify them to be able to describe how matter and energy relate to the curvature of space-time and how the curvature of space-time relates to the motion of matter. But this is Einstein's picture. Gravity is curvature.
So again, it doesn't say anything. Gravity is curvature. No, it's a convergence. So again, that still doesn't make any sense. You're saying curvature in 2 dimensions. But in 3 dimensions, there's no curvature. It's a straight line right for the center of the sun. That's how the Earth is moving. That's how that's what the mathematics dictates. Is, as Leonard Susskind would say, an anti-divergence. Okay, he doesn't want to say convergence for whatever reason, so he says an anti-divergence, and all that's saying is that everything heads for the center. Everything appears to be moving as if there was some fluid. Okay. That was a stream that was moving towards the center, and everything gets pulled by that stream. So there is this geometry argument falls apart when they start to apply it to 3 dimensions, because then it just becomes a convergence. And all you're talking about is how fast does it move towards that center point.
Gravity is curvature. The curvature of space-time is what we call gravity.
See, they're just taking 2 dimensions and saying we're going to use the 3rd dimension to represent velocity. So you have 2 dimensions, and they're just going to say, okay, let's use a bend in the line from these 2 dimensions, okay, this flat plane, and we'll just use this 3rd dimension to represent velocity. So instead of treating it like the real world, where there's really 3 dimensions, up, down, left, right, forward, back, where they have to account for something's motion, which is straight for the center. I mean, it's a straight line. Everything's traveling a straight line right for the center of the other object. So there's no curve in either the path. The real path it's going to take is not going to be curved. The Earth is not taking a curved path towards the center of the sun. It's taking a direct path. If you take an object and give it no velocity and let gravity pull it, gravity's going to pull it in a dead straight line. There's not going to be any curve. This does not curve to my hand, okay? It doesn't go from point A to point B in any curved lines. This is just nonsense. This is a gimmick.
That's his final theory. That is general relativity in a nutshell. And it comes from these thought experiments. Obviously, nowadays it's derived in different ways. We use different techniques and more rigorous mathematics to actually get at the equations of general relativity, but it comes back to these fundamental principles.
Yeah, more rigorous mathematics, which is almost laughable. More obtuse mathematics.
With the equivalence principle, examining it in different scenarios, looking at the effects of rotation, leading us to the conclusion that curvature has something to do with acceleration, acceleration has something to do with gravity, gravity...
So again, it really doesn't. Gravity has something to do with absorbing force, creating imbalance, and then forcing something essentially to move from high pressure to low pressure. You absorb the pressure doesn't exist, that means something's in high pressure, it has to move to lower pressure.
Has something to do with space-time. You thread all that together and you get general relativity. So, in this picture, all observers, everybody, a beam of light, our rocket ship, astronaut falling out of that rocket ship, it doesn't matter.
It all matters, so that's really where, again, this all fails, because we know the forces are doing one thing, which is perpetually moving at the speed of light. And the force essentially is the definition of energy, which means energy can't be created or destroyed, and that's essentially what you're saying about a photon. A photon goes into a system, it never dies. So if it's making the system move, or it's making the system hot, it's in the system, it's in there, it's in the system, and until it's released, it's going to be hot or it's going to be moving. And that's the rule. So it's a piece of momentum. So force is momentum. That's where all the momentum comes from. And if any matter bit has any force, it had to absorb it. It had to acquire it. The Earth is moving at a velocity. The velocity came from somewhere. All the little atoms had to have a velocity. All the stuff that made the Earth had to have a velocity, and they all had to get it from somewhere. So they all had to be exploded or shot or expelled through some event that shot one piece this way and shot another piece that way. It all started with balance, and we're on one side of the balance. One piece went that way. Well, I'm never going to see that piece ever again. But the piece that went this way, right towards me, is going to hit me. So one side of the equation is going to smack me right in the face. The other side of the equation is never going to be relevant to me. And that's fundamental to how all this shit happens in the universe, because we only see the part that affects us. Just as the space shuttle astronaut doesn't see the flames shooting out of the back of his space shuttle. That energy, he's disappeared. He's leaving the building of that energy.
People want to follow straight lines. They all do. But space-time underneath them is warped, and they're forced to follow different trajectories. And these different trajectories are what we call gravity.
So again, it's just a gimmick. It's just taking something, you're taking something flat, okay, in two dimensions, and you're saying, let's make the third dimension represent something different than what it should be representing. So instead of up and down, you're making it represent fast or slow. So the more you point the line in a direction, the more you're saying the faster it's going. So that's how you create your wells of gravity. And the big liability of this wrong model is that you can create some kind of infinite amount of gravity by just digging wells deeper. But there's no evidence that there's an infinite amount of gravity that you can create.
It's the bending of space-time itself. So how does it do it? Like, how does space-time bend in the presence of matter or energy? I don't know if that's the right question. Because...
Yes, because you don't have an answer to the simple question. It's not, where's the energy come from would be another simple question. How can you have movement without a force? So what are you talking about? How is this physics? You're pretty much abandoned physics, and you're just telling me spooky action runs the universe. The universe is controlled by spooky action.
General relativity, the presence of matter or energy, is the bending of space-time. How does the bending of space-time alter trajectories?
So again, how does energy bend space-time? So another thing for which there's just absolutely no evidence that the energy itself is also bending something and creating energy. I mean, that doesn't make any sense. The energy is the consequence of the bending of the space-time. You can't make space-time make energy and matter. I mean, that's just silly.
In cause acceleration, well, the bending of space-time is gravitational acceleration. They're the same thing. They're connected through these very...
So it is acceleration. Get rid of the word gravitational, because we know the only key part is acceleration. So we have acceleration without a force. Acceleration without a cause. You're just saying spooky action geometry tells it where to go. Complete nonsense.
Fundamental assumptions about the way the universe works. That is general relativity. That is our modern picture. And it's
garbage, yes. And as a picture, it's garbage. As a mechanical explanation, it's garbage. I don't know why all these people who seem like reasonable engineering types, mechanically inclined, how any of them fall for this crap. I mean, I read Popular Mechanics as a kid. There's none of this spooky action crap in there. There's nothing. This is just crap. This is a garbage, convoluted, phantasmagorical. This is a story. This is not truth. This is not evidenced science. This is just made up crap. It's crap. Even if it wasn't made up, it'd still be a stupid answer. It's silly. It's overtly fake.
Such a unique viewpoint. It's really hard to argue. It's really, really, really hard. If we lived in a universe without Einstein, it's doubtful that anyone would have come up with general relativity. Because
so they're hilarious right there, right? I mean, that's almost, that's funny just because, nobody else could have gotten away with it. It's only because of this perfect circumstance, the whole German war thing, all this stuff, all the crap that went in to make this little perfect cake of bullshit. And you fell for it. So it just happened to be a really good con. Magic tricks work a certain way, I mean, anybody can do one. But you have to have perfect conditions to pull off an elaborate one. And it just happened that the conditions were right, that everybody got duped by a really piece of crap.
At the time, special relativity, there were other people thinking along similar lines. In fact, Einstein took a lot of the existing mathematics, he just gave it a different twist, a new interpretation. So someone else would have figured out special relativity, but general relativity?
So you just said it, and now you're saying it again. Oh yeah, but general relativity. Right. No one else could have gotten away with it. I'm sure other people could come up with silly analogies. Again, I don't think Newton was unaware of some idea that you could mimic gravity by putting a weight on a tablecloth. I'm pretty sure he had the idea that that would simulate some aspects of gravity, but it only simulates some aspects because there's friction all over the place. A lot of things why it fails, and you're not going to create the right curvature by luck alone. You're going to have a very specially constructed fabric to create the right proportional curvature.
That's all Einstein, man. That's just him. And it's doubtful if even today, in the 21st century, we would have this picture of gravity if it weren't for Einstein. And it was his thought experiments connected to...
So again, and it's just such a perversion. It's so distant from what Einstein was seeking, which was this mechanical explanation. I mean, again, the ironies here are so in your face. Here it is, Einstein complaining about spooky action, and his relativity theory is based on spooky action. It's not a mechanical theory. It's not a mechanical description of why. It's just a rephrasing of what happens. It's not an explanation of why it happens.
His extreme perseverance and mathematical agility and competence that gave us this. Next time I'm going to...
Gave us nothing. Again, it's of no relevance in any sense whatsoever. I mean, astronauts don't use it because it's uselessly complex math. You gain so little from it. and in terms of precision. And you gain just as much from realizing that gravity has a speed. Like I said, that was half the errors that Newton made. Half the absences of Newton's theory was just because he didn't know how fast the force moved.
Talk about how we test this fantastic idea of general relativity, that gravity is curvature.
Right, and you don't have any of those tests. All you have is time dilation. And again, that's a separate subject. That just has to do with, does velocity break clocks? And I would give you the obvious answer, yes. Clocks don't tell time. Time doesn't change and the clocks are telling the right time. No, the clock breaks. Time is still exactly what it was before. Your clock's broken. And we are a biological clock. So you will break us also if you oblige us to travel too fast. But there will never be any, the proportions will always be different. How things break won't have any proportional relationship. Humans will die if you attempt to accelerate them at the speed of light or anywhere near it. They'll die. They won't grow old slower. They'll just die because the biological and physical processes will break down. Every clock will break differently.
That's next time. Hope you enjoyed. If you like this video, feel free to hit the like button and also subscribe and do the notification.
Yes, and do all this other crap that somebody with a half a brain shouldn't need to be told what to do. So people who are supposed to know something about physics are supposed to be watching these videos, and yet they're so fucking clueless. They don't know what a subscribe button is. They don't know what an email address is. They don't know what a donate button is. They're that fucking stupid. They need to be told all this. Oh, please hit the thumb up. Oh, please ring the bell. Oh, do this. Oh, do that. They have to be told all this crap. And they're watching physics videos. That's just pathetic. You know, it's pathetic that you think your audience is this stupid. Alright. Or that you would want an audience that stupid. I guess it's more to the point. I want those people to go fuck themselves. If you're so stupid, I need to explain what a subscribe is, and I have to explain what a thumb up is. If you're that fucking stupid, I want you to go the fuck away. I want to offend the shit out of you. I want you to hate my guts. I don't want you to hang around. Alright, so that's enough of that. So, till the next time and such, so forth and whatnot.